Hello everyone. In this lecture we will start with alternating current or AC. Previously in this semester what we have learned so far, everything was related to DC or direct current. So the basic purpose of this lecture is to understand the difference between alternating current and direct current and how that makes calculating or analyzing AC circuits quite more difficult compared to DC circuits. So let us start. First of all, let us briefly understand what is the basic difference between direct current and alternating current circuits. So in DC circuits, we saw that when we had any kind of quantity like voltage, current, everything was constant with respect to time. Like we have this graph here, in the horizontal direction we can see the time, and here we have plotted a current, value of current, and that value is actually constant for DC case with respect to time. It will have a fixed value. And this can be said for all other quantities in DC circuits. Like let's say if it was a voltage, that should also be constant throughout the time. So that is direct current or DC. Now for alternating current, what we are going to see is that it will change with respect to time, and what will change is basically the magnitude and also the direction of current. So here this is an example of alternating current. So again we have in the horizontal axis the time, and in the vertical axis you see we have a periodical signal that is changing with respect to time periodically. So at the same time the magnitude is obviously changing, as well as the direction is changing. Here you see this portion is positive, this portion is negative, so both magnitude and direction should be changed, and also it should happen periodically. Then we can call this kind of currents as alternating current. So that is the basic difference between direct current and alternating current. Now here let us look at this graph to understand which signals can be considered as an AC signal. Like for the gray signal, it has no periodicity, it is abruptly changing, as a result it is not an AC signal. Then what about this blue signal here? It has periodicity, the magnitude is changing but not the direction. As a result this is not an AC signal, this is called pulsating signal. Then the red one is obviously a direct current signal, because the magnitude as well as the direction is not changing here. But the green one here, obviously the magnitude is changing as well as the direction, and this is happening periodically. So the green one can be considered as an AC signal. Now another question may arise is that theoretically we have understood what AC signals are, that it changes its magnitude as well as direction with respect to time. But physically, how does that look like? To understand that, let us look at one simulation here. So here you can see that we have an AC source here, and we have connected a resistor in series with that. So physically what happens is that the polarity of this AC signal changes with respect to time. So for this terminal, some of the moments this terminal has positive value, this one has negative value. For other moments maybe this will have negative value and this will have positive value. So this polarity will be changed back and forth with respect to time, and as a result, as you can see, the current is also flowing forward and backward. So in this way, in an AC circuit, both voltage and current both changes its direction as well as magnitude with respect to time. Now let us discuss some basics about sinusoids, because all the AC signals we are going to use for analysis is sinusoids. So here we can see this is one sinusoidal signal which is V of t, and it can be represented as Vm sin omega t. I think sinusoids were discussed in your intermediate level, but still I want to repeat those so that we are in the same page. So this Vm here, this is the amplitude of the signal. So the maximum value here or the minimum value here, that is actually the amplitude, right? And omega is the angular frequency in radian per second. So what is omega? To understand that, let us try to find out the total time taken to complete one cycle, and let us call that T, okay, capital T. So we are calling that the total time taken to complete one cycle up to this, and in that time the amount of angle covered is obviously 2 pi radian, as it is written here in the horizontal axis, right? We can also say in degrees, that is 360 degree. So if this is angular frequency, we can simply say that omega is equal to the total amount of angles covered in one cycle, and in the denominator we can say the total time taken for that, which is T. So in this way we can find out the value of omega. So this is angular frequency. We have another thing which is called cyclic frequency. Cyclic frequency is how many cycles we complete per second. So in that duration T, we have completed only one cycle. So we can say 1, the number of cycles completed, divided by the amount of time taken, which is capital T. And we can actually make a relationship between this omega and F by placing this T value in this one, right? If I do that, we will get something like this. Omega is equal to 2 pi F. And in general, when we quantify a signal, we will have these two parameters very important, which is F, the frequency of the signal, and also another one is this amplitude of the signal. The frequency of the signal for our country is 50 Hz. That means it changes its direction with respect to time 50 times a second, and that happens 60 times a second in USA. So these are some of the basics of sinusoids. What is amplitude, what is angular frequency, what is cyclic frequency. But there is another thing which is called the phase. When we have two different signal, we can compare between them what is the phase difference between them. So here we can see we have two different signals, V1, which is Vm sin omega t, represented by this red line, and V2 is this one, right? V2 has some phase difference compared to this one. So when we are saying phase difference, there is a difference here. That means to have phase difference, we need to have two different signals so that we can compare between them. So here we are seeing that because of this plus phi here, this signal is ahead of the previous signal V1 by this phi angle, right? So in electrical engineering, our way of representing that is, we will say V2 is leading V1 by this angle theta, okay? Or another thing we can say similarly, that V1 is lagging V2 by this angle, same thing, right? So this will come up every now and then, the phase difference, because we will see in AC circuit we will have different quantities, different value of voltages, different value of current. All of them will have some phase differences, so we will have to compare those. Now before we move on to discussing details of AC signals, first of all we need to understand the basics of capacitor as well as inductor. Because previously when we analyzed DC circuit, there was only one passive element, resistor. Now here in AC circuit we will see there is resistor as well as capacitor and inductor used as passive element as load. So what is capacitor? In simple terms, a capacitor consists of just two conducting plates separated by an insulator or dielectric. Generally that insulator is just air. So we have these two plates here placed very close to each other. There is some gap between them, and generally what we do to increase the capacitance of this device, this capacitor, we actually provide some dielectric material that provides more capacitance for this device. Now how does it work? To understand that, just understand that for two of the plates we will connect a voltage source here, one terminal connected with this one, another one with this one, right? As a result, what will happen? Obviously the positive charges will be repelled here and will be stored here in this plate, and negative charges will go here and will be stored in this plate, and because they are placed very close to each other, the positive charges will attract the negative charges, so it will create some kind of equilibrium, and when we will have enough amount of charges so that no more charges are flowing here, that is the final equilibrium, right? And we actually represent that equilibrium as the amount of charge stored, okay? The amount of charge stored is proportional to the voltage applied. And to equate these two portions, what we do, we use a proportionality constant here, which is called C, or capacitance. Now this capacitance here, the value of this depends on the material of this device. So we can represent C as something like this. C is equal to epsilon A divided by D. So A here is the area of these two plates, okay? Individually, each of these plates have some area, that is A, and the distance between them, that is D, the distance. And in between them, we will have some dielectric material, or sometimes maybe air. The permittivity of that material is epsilon, okay? And finally, after calculating all of those, we are going to get the value of capacitance here. Now, we should understand what is the characteristics of capacitor to understand where it will be applied. So this is the symbol we use to represent capacitor, and general convention is, obviously, there will be some voltage, across the capacitor, and generally the convention is whenever the capacitor is storing charges, then the current direction will be such that it is going through this positive terminal of the capacitor. So now we want to look at some important observation based on this capacitor, which will actually clarify what is the purpose or what is the application of this kind of devices. The first observation, to understand first observation, we need to first derive something. That is the relationship between the current and voltage of capacitor. So what I mean by that is that whenever we have a voltage across this capacitor, what should be the value of current through that? What is the relationship between that? Like we had for our resistor, like Ohm's law defined V is equal to IR, right? V is equal to IR. That means we have a proportional current for the voltage across a resistor, right? So can we have the same kind of equation for this capacitor also? To derive that, what we can do is we can actually look at this equation here, which is I is equal to dq divided by dt. So the amount of current should be equal to the rate of change of charges. And previously in the previous slide, we derived this one, Q is equal to CV, the relationship of charge and voltage for capacitor. We can just place this value here, right? If we do that, what we will get, we are going to get something like this. And here C is a constant because it doesn't change with respect to time. It just depends on the material and properties of the capacitor itself. So we can write something like this, I is equal to C dV by dt. So here these things is actually representing the change of voltage with respect to time across this capacitor, right? And this is the current through that capacitor. This is a constant. So based on this formula here, we can understand some characteristics of capacitor, some very important observation. The first observation is what will happen when we have a constant voltage across this capacitor. If we have a very constant voltage across this capacitor, obviously this particular portion here, dV by dt, this value should have a value of 0, right? As a result, the current through that should also be 0. That's why, when the voltage across a capacitor is not changing with respect to time, current through the capacitor should be 0. This is the reason why capacitor acts as an open circuit to DC, because the voltage is not changing with respect to time across this capacitor. As a result, no current should also flow through there. There will be some current flow, like when you actually start the circuit, no charges are stored here. As a result, some charges will flow towards that, right? And as a result, at that moment, because of the charge flow, there will be some current. But after the equilibrium, there will be no current. This capacitor will act as an open circuit to DC. So that is first observation. Now for the next one, we need to draw some graph. Let's say if I apply a voltage which looks like this, okay, which maybe looks like this. So if I apply this voltage across this capacitor, then how should it behave? If you remember, we know that when we calculate a derivative of a function or a graph like that, it just basically calculates the slope of that. So obviously, if I just try to calculate the derivative of this particular portion here, that will be infinite because the slope of this portion is infinite. So if I apply this kind of voltage across this capacitor, then this portion dV by dt, this should be infinite. As a result, the value of I required is infinite. We have to provide infinite amount of current theoretically. That is not possible. That is very difficult, right? So as a result, what happens? It will actually prohibit that, and across this capacitor, you are going to see this kind of behavior, something like this. Okay, it will not abruptly change its voltage, rather it will change gradually, something like that. So that is what it is written here. The voltage across a capacitor cannot change abruptly. So capacitor resists the change of voltage. That is capacitor's characteristic. Okay. Now, in the similar way, let us try to understand the basics of inductor. Now, what is an inductor? An inductor consists of a coil of conducting wire. So if we have some wire and we make a coil out of that, that will be considered as inductor. Simple as that. And here, this is actually a formula for calculating the inductance of an inductor, and all the parameters here depend on the materialistic properties of this device. Like we have length here, the cross-sectional area here, and we can also provide some core material here, which is made of ferromagnetic materials, and also we have the number of turns we have for this coil, and using these parameters here we can find out the value of inductance. Simple. Now what we want to understand is the characteristics of an inductor. Now to understand the characteristics of inductor, we can take help from Faraday's second law of electromagnetic induction. From that we can derive that the voltage across an inductor is proportional to the change of current through that. And to equate these two portions, we have just used this proportionality constant, which is L, or inductance, this one, right? Based on the property of, or materialistic property of this device basically. Now using this formula here, we can understand the characteristics of an inductor just like before. This is the general symbol we use to represent an inductor. Here the value is L, and general convention here is when the inductor is storing energy, at that moment the current is going through that positive terminal, just like before. Now from the previous page we had this formula, V is equal to L di by dt, right? V is the voltage across the inductor and I is the current through that inductor. Now based on this formula here, we can have some observation of inductor. First thing is, let's say if we have a condition where we have a constant value of current through our inductor. If this current is constant with respect to time, what should happen to the voltage here? Obviously, when we have a constant current, the value of derivative here, di by dt, should be equal to 0 because the current is not changing with respect to time. So then obviously the voltage across our inductor should also be 0. And from this we can understand that when the current through an inductor is constant with respect to time, the voltage across the inductor is 0, right? Just like for your DC case. So in DC case, obviously the current should not change with respect to time. As a result, if we actually measure the value of voltage across this inductor, that should be equal to 0. It should not have any kind of value. Obviously, just like before, when you start the circuit, some currents will flow, it will gradually increase, and at that moment something will happen here, there will be some voltage across that. But after the equilibrium, there will be no voltage across that. That is the first observation. And for the second observation, again we are going to do the same thing. Previously we had applied a voltage across the capacitor. Now what we are going to do, we are going to flow some current through our inductor, and the behavior of that current should be something like this. This is the current. Let's say we used a current source to apply that current through that inductor, and the behavior of that current is something like that. It is abruptly changing from 0 value up to a very high value abruptly. And if I apply this current through this inductor, what should happen to inductor? Obviously, again the same thing here also. For this portion, the derivative or the slope is infinite. As a result, this portion here will have infinite value. As a result, the value of V or the voltage across the inductor should also be infinite. We have to provide infinite amount of voltage for this to happen, which is not possible. So what will happen across our inductor? We are going to see that through our inductor, the current cannot change abruptly like this, even if we had applied a abrupt current like that. So it will change something like that. So it will gradually change up to the maximum value. So that is the second observation. The current through an inductor cannot change instantaneously. It will gradually change, and the time taken here, this is important also. The time taken here to get to the maximum value, that depends on the value of inductance. If it had higher inductance, then maybe the graph would be looking something like this. So it will take more time to get there. Same goes for the capacitance also. If the capacitance is higher, then the time taken to charge or discharge is higher. So these are some of the property of inductors and capacitor. For capacitor, the most important factor is that it resists the change of voltage across that, and for inductor it resists the change of current through that. So now we can move on to discussing the details of AC circuits. So let us go there. So here we have an AC source with resistor. Very simple circuit. We are going to analyze this. Now in this circuit, you can see that we have actually used an AC source. This is the symbol we are going to use to represent AC source, and the value of that voltage is Vm cos omega t, V of t, and we have connected a resistor in series with that. The voltage we are getting across that is Vr of t, which is exactly equal to V of t, obviously, because we don't have any other elements here. And based on that, we can calculate the value of current IR of t, current going through this resistor. And this is just simple basic Ohm's law. We only have this resistance here. We can simply say IR of t is equal to Vm by R cos omega t. And based on these calculations, we can have some observations for resistor in AC circuit. In this graph here, with respect to time, we are plotting all the signals. Like we have the voltage across this resistor here, then the current through that resistor here, the value of resistance, everything is here. So from that you can see that if I take the ratio for any point of voltage divided by the current, like for this one or this one, for all the cases, what we will see is that the ratio is constant, and as a result we know the ratio of voltage and current is the resistance. So that's why R is constant, it is not changing with respect to time for resistors. So resistor acts very similarly with AC circuit previously, as we had seen for DC circuit also previously. So that is first observation. Then for the next observation, think about R, the value of resistance. If I plot the value of resistance with respect to frequency, then obviously again we are going to see that the value of resistance is constant. It is not changing with respect to time. It is not a function of time. It is not a function of frequency. It will be constant throughout the time. So two observation. First observation was it is constant. The value of resistance is constant with respect to time. Now here we are seeing that it is also constant with respect to frequency. Now the third observation, in this one, let us look at the two graphs for resistor. Just for resistor, the voltage across that is V of R, a cos signal with an amplitude of Vm. And for IR, it is also the same type of signal cos omega t, but with a different amplitude of Vm divided by R. Now, can we see any phase difference between the voltage and the current for this resistor? They have exactly the same phase difference of 0, right? Because both of them are cos signal. So the third observation is that for resistor, for this kind of circuit, we are going to see that there will be no phase difference between VR and IR, the voltage across the resistor and the current through that resistor. This will have same phase. Now, why did we discuss about this observation, the three observations we had for resistor? Because now we will see that for capacitor as well as inductor, these behaviors are very different. As a result, we cannot calculate or analyze AC circuit just like your DC case. There will be more complications because of the behavior of capacitor and inductor. So first, let us discuss about capacitor and have those observations. For capacitors, we have this simple circuit here, and we are again applying the same AC signal, V of t is equal to Vm cos omega t, and we have a capacitor here. Again here also we are saying that the voltage across our capacitor is Vc of t. We can simply say Vt is equal to Vc of t. Now, from our previous understanding of capacitor, we said that this equation can be written. The current through a capacitor is equal to C multiplied with the derivative of voltage across that capacitor, right? So that is this Vc and Ic, right? Vc can be written as V of t. These are two equal, and we can just simply replace the value of V of t or Vc of t here, which is this one. Now here inside of this derivative Vm is constant. It is not changing with respect to time. Amplitude is constant. Because of this parameter we are seeing the change. So we can just put this value outside of this derivative. Then we are going to take the differentiation of this one. Differentiation of cos omega t is minus omega sin omega t. So we have this final derivation. So we can say the current through that capacitor IC is equal to minus omega c Vm sin omega t. So we have found out the value of current here, and also we had the value of voltage across our capacitor. Now what we want to find out is the resistance like property of capacitor. Obviously resistor had some property that it resisted the flow of current. This capacitor will also have this kind of behavior. So we can also represent that, but we cannot actually say that is resistance, because resistance is for resistor. So for now we are just saying that this is resistance like property. So how to find that out? First of all, this resistive property we are saying of capacitor, we should call that Xc. And to find the value of Xc, we will take help from Ohm's law. In Ohm's law, to find the resistance of any element, we just calculated the value of voltage across that divided by the current through that, right? Again, here we are going to do the same thing. So the voltage across our capacitor divided by the current through our capacitor, and we had already calculated these values here. We will just put those, and finally this resistance like property comes as this value, 1 divided by minus omega c cot omega t, right? So this is the value of resistance like property, or later on as we will call that reactance. Okay. Now as we have calculated all the parameters we need, we can move on with our observations for this circuit. So in this circuit we have found out the value of voltage across our capacitor, then the current through our capacitor, and also the resistance like property of our capacitor, which can be called reactance, right? Now in this graph here, these three parameters are actually drawn. The green one is the voltage, then the blue one is the current, and this orange one is basically the resistance like property of our capacitor. So this is a cot signal. As a result, this should look like something like this. Now if you observe this signal here, this resistance like property, this is also changing with respect to time, right? Periodically. So if you just look at here, like let us observe here how, because of the value of this resistance like property of capacitor, the value of current is changing. So this value is going from minus infinity to 0 up to plus infinity, right? And because of that here, because of this minus infinity value of resistance like property, obviously minus value has no significance here. This is a theoretical calculation, so very high resistance you can say, and because of that the current through our capacitor is 0 here, right? And for this portion here, if you look at this portion, the value of resistance like property is 0. As a result, we have the maximum value of current through our capacitor. Again here you are going to see we have a very high value of resistance, and as a result we have again 0 value of current through our capacitor. So in this way, because of this variable resistance like property of our capacitor, gradually the value of current is also changing with respect to time. So that is the first observation for us, that the ratio voltage divided by current, or we can also say that is Xc, the resistance like property of capacitor, this is changing with respect to time. This is not fixed, just like your previous case. In our previous case, our resistor had a fixed value with respect to time. Now let us look at the second observation. Now here if we can plot the value of Xc with respect to frequency, the resistance like property with respect to frequency, then how should that look like? This was our formula of Xc, and in the previous case, if you remember, we had observed the value of everything that is changing with respect to time, but the frequency was fixed because this parameter here, this is fixed from the get-go. So if we have 50 Hertz frequency for our appliances, that is fixed, that is not changing with respect to time. So we had fixed frequency, but the time was changing. Now think of an imaginary case where we could freeze the time, but just look at how with the change of frequency everything is changing. Okay, that is what we want to do here. We are going to freeze the time domain. So if I freeze the time domain, obviously it will have a fixed value, it will have no significance. Then we are going to analyze or observe this portion here, and this portion here can be written as something like this. Xc of t is equal to 1 divided by minus 2 pi fc. So here Xc is inversely proportional to frequency, right? As a result, we have this kind of curve here. So from this curve we can understand some behavior of capacitor in AC signal. Like, let us look at this portion here, this particular portion where we have frequency is equal to 0. For frequency is equal to 0, we have infinite value of resistance like property or Xc, and this value of frequency 0 represent DC signal. So for DC case, we can say our capacitor acts as an open circuit because infinite resistance means open circuit. And as this value of frequency increases, the value of Xc decreases up to here. So theoretically, if we can have infinite value of frequency, then we are going to get 0 resistive property for capacitor. That is possible, right? So now for this frequency change, the resistive property is not fixed anymore. It can change with respect to frequency also. So that is our second observation. Now let us look at the third observation. So here we have only drawn the voltage across our capacitor and the current through our capacitor. So here the two equations are written for VC and IC. The equation for IC can be written something like this, so that we can compare VC and IC in terms of phase. So clearly we can see that the phase of VC and IC has 90-degree phase difference, and that is observable in the graph also. We can see that we have pi by 2 phase difference between the voltage and current, and specifically the current is actually leading the voltage here across our capacitor. So that is the third observation. Always we will see for a capacitor there will be some phase difference and current will lead the voltage by 90-degree. So these are the three observations we have for capacitor. The first one is that with respect to time, the resistive property of capacitor changes. Second one was with respect to frequency also it changes. And for the third one, because of this behavior of this resistive property, we can see that the current and voltage of capacitor has some phase difference, right? Now we are going to do the same thing for inductor also, same analysis. So we have this circuit here, and we have supplied the same voltage V of t, Vm cos omega t, and we are going to calculate the voltage across our inductor, the current through our inductor. What is that? So obviously just like before, calculating the voltage across our inductor is very easy, which is exactly equal to V of t. And for calculating the value of current, previously we learned that the voltage across our inductor can be written as L multiplied with the derivative of the current through that, right? So that is what we can use to derive the value of current here. So we will just take the value of current, and if I move the derivative in this portion here, we will see that we will have this expression here. So differentiation has become integration here, and the value of VL is exactly equal to this value because VL is equal to V, and we are just going to place that value of VL, then take the value of Vm outside of this integration because Vm is constant with respect to time. Then we have to integrate that, and this integration results in this value 1 by omega sine omega t, and this is the final value of current through our inductor. Now, just like before, based on the value of our voltage and current, we can find out the value of resistance like property of inductor. Again, here also we can call that reactance, and the name we are going to give this one is XL of t. And we just put the values of voltage and current here that we had found out, and finally the resistance like property of inductor comes as this one, omega L cot omega t. Now we can again start our analysis or observation. So the first observation, just like before, we are going to plot the three graphs, one for voltage, one for current, one for resistance, right? So here you can see like for voltage and current we have plotted, obviously no problem, and for the resistance like property or XL, this is also again a cot signal, so it will have this behavior, periodical behavior. So it will go from infinity to 0, then to minus infinity, and it will happen continuously, right? And again here, let us try to observe because of that what is happening to the current. Like here for this region here, because we have plus infinite value of resistive property, we will see 0 amount of current is flowing. Then for here you will see that the value of resistance like property is 0. Because of that, here we are seeing maximum amount of current, then here also very high amount of resistance, as a result 0 amount of current. So again here the ratio, obviously the ratio of voltage and current for each time is changing gradually, right? And as a result we are seeing this kind of graph for resistance like property. It is not fixed. So with respect to time, again for inductor, the value of resistance like property is changing. Now for the next observation, we are going to do the same calculation for frequency. So how our resistance like property of inductor is changing with respect to frequency. So again here we are going to freeze this time domain portion. We are going to imagine as if the time is frozen. Only thing that can change is the frequency, right? So we are going to rewrite this portion, x of L is equal to 2 pi fL, and here this x of L and f are proportional to each other. So if I want to plot the value of XL with respect to frequency, that should be a straight line like this because it is proportional. So again for inductor, if I change the value of frequency, the value of resistance like property of inductor will change, but differently compared to your capacitor. So let us try to observe, like for this case, for here, in this case we can say frequency is equal to 0, like for DC case. For DC case we are seeing the resistance like property is also 0. As a result, for DC case inductor acts like a short circuit. And then as you gradually increase the value of frequency, the resistance like property can also increase. And theoretically, if you can increase up to a infinite value of frequency, we will have an infinite value of resistance like property. So in this way it can change. Now let us look at the third observation. Here again we are just taking the voltage and current for the graph, and we want to observe the phase difference between these two. Unlike before, unlike capacitor, you can see there is some phase difference here, but that is quite different compared to capacitor case, because previously capacitor current was leading the voltage. Here actually the current is lagging the voltage, right? So that is what we are going to see. Even if you take the formulas of these two equations, this particular formula of current can be represented something like this. From these two things here, this one and this one, we can clearly see there is a clear phase difference between the voltage and current, but the current here is actually lagging by 90 degree from our voltage. So that is the difference between inductor and capacitor. They both have 90 degree phase difference, but for capacitor the current is leading, for this one the current is lagging. Now just for one last observation, we are going to look at this circuit here where we have a resistor in series with an inductor, and this is the AC signal we are providing. Now for this case, if I want to find the value of current through this circuit, we have to form a KVL equation here, right? And obviously the voltage here added with this one should be equal to the source voltage. So the voltage across the inductor is this one, because V is equal to L di by dt, and this voltage drop is Ri. So finally we will get this equation. Clearly this equation is a differential equation, and we all can understand that solving a differential equation is quite more complicated compared to what we had for DC cases, right? And this is just for one resistor with an inductor in series. Think of a circuit where we have multiple sources, multiple passive elements interconnected with each other. There will be more difficult differential equations to solve. So that is the main reason why solving AC circuits are quite more difficult compared to DC circuits. And this is the reason why we cannot take the traditional approaches we had for solving DC circuits if we want to solve AC circuits. And I'm not going to show you the process of solving this one using differential equations or whatever, but if we can solve that, this is the value of current we are going to get. This is the formula. Now using this equation of voltage and current, what I want to show you is that how the behavior of current changes if we change the value of R or L in this circuit. So let us try to observe that. So in this graph here, we have plotted the value of voltage for that circuit and also the current flowing through that circuit. And here we can actually change the value of resistor and also inductor in our circuit. So initially the value of inductor is kept as 0. As a result, we can consider our circuit as a purely resistive circuit, and for a purely resistive circuit we know that there should be no phase difference between voltage and current. And as we change the value of inductance gradually, we are going to see that it is having some phase difference with respect to its voltage, right? And as we keep increasing again and again, if we have a very high value of inductance, we are going to see that it has almost 90 degree phase shift with respect to the voltage. You see the phase difference with respect to voltage is almost 90 degree. So in this way, when we have combination of different passive elements like inductor, capacitor and resistance, we are going to have phase difference between 0 to 90 degree, and based on the value of capacitor and inductor, either current can lead or lag, right? If we can understand all of these things, maybe in the next lecture we can move on to the approaches we use for solving AC circuits, particularly the phasor algebra and their application in AC circuit. But what I want to briefly explain is that, we had seen that for each of the quantities we had in our circuit, like we had voltages, we had currents, we had, resistive properties, everything was changing with respect to time. But one thing was common, everyone had the same value of frequency. If you look at here, this is omega, this is also omega, this is also omega. So they are actually moving with respect to time, but they are moving in the same direction with the same speed. So with respect to each other, they are kind of stationary. So can we take that idea to solve this kind of problem? We know that for DC circuit, all of them are stationary, no problem. That's why we can solve them very easily. But these quantities we have here for AC circuit, they are actually moving with respect to time. But they are stationary with respect to each other. So if we can somehow freeze the time, then solve the problem, then again take the parameters we had frozen earlier previously, then maybe we can retrieve the results we had desired, right? So this is the basic understanding. Somehow we are going to, omit these portions here, the portions with time quantity, then we are going to solve our circuits, and finally when we have the results we want, we are again bring back our time parameters. Well, this was just a mere introduction to AC circuits. Um, I think understanding and solving AC circuits can be quite more complicated compared to DC circuit. That's why I wanted to make this video, so that at least we can understand what is the difference between these two and what makes solving AC circuits more difficult than DC circuits. So that's all for this lecture. Thank you.